was off the hook. Thanks so much, Adrienne, for finding a time slot for me to speak. And thanks in particular to those of you that have hung around this late on a Friday afternoon. Some of you in particular, given that it is rather late now on a Friday afternoon, I truly appreciate it. So I'm with CEMI, or the Center for Excellence in Mining Innovation in Sudbury. And our purpose is to help address the research and development needs of the underground mining industry by engaging with and coordinating the activities of others working in that R&D space. Specifically, I mean researchers at universities, researchers at research institutes, at service and supply sector companies in the mining space, and indeed at the mining companies themselves. We like to think of ourselves as the organization that comes in to help scope projects, coordinate the various partners, and in some cases, even fund the initiatives. So, in the ultra-deep mining network environment, that is, amongst those miners that are working at below about 2,000 meters in our mines, or about 8,000 feet, there are a series of problems which face us. And they have to do, among other things, with heat, with geotechnical stresses, and with the amount of time to which we can safely allocate to workers and expect them to be productive. I might argue that there's a fourth very significant risk based on those other three, and that includes overcoming somehow the economic risk of being able to operate at those depths at all. But today, what I'm going to do is talk about a program within CEMI called the Ultra Deep Mining Network that's got a, among other things, focus on helping to address the energy needs and the challenges associated with energy use in ultra-deep mines. So quickly, the Ultra Deep Mining Network is a $46 million initiative. It's been around since about February of 2013, and it's funded by a multitude of partners, not least of which is the federal government, to the tune of about $15 million, with the balance coming from other areas. Those other areas include the mining industry itself, the research community, and interestingly, the service and supply sector, or the small to medium-sized enterprises throughout Canada with an interest in helping the ultra-deep mining industry. From them, a total commitment on top of that $15 million from the federal government amounts to almost $47 million for this 5-year initiative that began in February of 2013. There's a list of all of the folks that are involved with this. You don't need, of course, to look at that in any detail. The message here is that there's lots of people involved. There are 28 projects that are currently underway, spread across 4 themes that I'll talk to in a moment. Interestingly, what this business model for this program is focused on is not doing a research and development in the sense of creating new knowledge, but in the sense of creating tools and technologies that are commercializable and for which people are prepared to pay something, specifically those people being the ultra-deep mining network. So those 4 themes that I spoke about are listed there. I have direct responsibility in my role at CEMI for themes 1 and 2, they being rock stress risk reduction and energy reduction, respectively. So what I'm going to do now is focus at a high level on what initiatives are underway in the energy reduction space. So for us, and we're supplementing in part some of the work that you've already heard about from Dr. Dean Miller just a little while ago. For us, it's all about trying to support projects and make them happen and be successful that will help take the ultra-deep mining network toward being able to say by 2040 it has reduced its energy consumption over 2013 levels to about 40%. And to that extent, the projects that are being supported are in two key areas. They're in the area of optimizing deep mine cooling technologies or creating new ones. And they're in the area of the electrification of underground equipment and just how that may be assisted to become more accepted by ultra-deep miners as a way to power, in particular, LHD fleets going forward. So there are 7 projects under this theme 2, or energy reduction theme, at UDMN, and they have a value over 5 years of just under $6 million. Of that, some $3 million is being funded by UDMN. The balance is being funded by the proponents themselves or others with an interest in those specific projects. What I'm going to do first is talk about the top list of projects there. It's really not important that you be able to read the small print on the right there, except to understand that what these projects are about is looking at current techniques for optimizing how we cool deep mines and how we might be able to improve that. The problem is quite simple in our deep mines. Existing refrigeration systems are expensive to not only build, but to operate. Furthermore, when they are operating at our mines, a great deal of heat is created by them, which in turn is rejected and wasted. There are many opportunities at our existing mines. Some of these opportunities are taken advantage of, admittedly, but by and large they're not, where geothermal energy potential is grossly underexploited. The perception amongst at least the Canadian mining industry, deep mining industry, is that geothermal energy as a potential source of heat is too costly and too much and too risky to try to take advantage of. The other perception, and we'll talk about this a little later, is that electrified equipment fleets likewise are not only too costly, but because of that and because of the perceived technology readiness level are also too risky. We'll talk about that in a moment. Let's first talk about these problems, however. One of the solutions that we feel needs to be focused on, and we're working with a team at McGill University to try and address this, is how existing freeze plants used in underground mining and tunneling operations might be optimized. There's a belief among the researchers involved in this particular project that there's a great deal of work which can be done with existing users of this technology, and one of the users in Canada, by the way, with which we'll be all familiar, is Cameco at its McArthur River mine in Saskatchewan. There's a perception, at least, that there's optimization of that technology, which, if it were to be employed, could greatly improve its effectiveness and its economics. And so the McGill researchers are hoping to access data from underground operators, be they tunnelers or miners, where freezing is used for ground stabilization, for example, so that they can help them optimize their processes. There's the perception that modeling of the freeze holes will enable better management of those freeze hole systems, those freezing systems, and that heat extraction can be improved for the purpose of making them more economic. There's a potential for energy savings by using heat generated or waste heat generated by those systems. And furthermore, if that heat can be collected, it can be used for a useful purpose, such as space heating or ventilation heating for surface facilities. So the research objectives of the McGill team on this particular project are to instrument and monitor an existing freeze plant somewhere so that a proper system performance assessment can be conducted, so that more accurate models can be established which draw attention to the opportunity for design improvements going forward when freeze hole systems and freeze wall systems are required in underground operations. They also feel that by looking at existing operating practices at tunneling operations and mining operations where this technology is utilized, that there is a great deal of opportunity to change those practices that will reduce in a lower electricity consumption and thus cost. Geothermal resources and how they might help all of us, including in our own homes, to reduce our energy consumption are, it is felt by the same McGill research team in this case, underexploited and underutilized. And that's perhaps because they're misunderstood. A very simple system shown on the right there of 2 holes in the ground going to some depth below ground and connected via heat exchanger to a house offer an example of how the temperature difference between the top and bottom of boreholes drilled even in your garden can be used to, when heat exchangers are utilized, potentially heat and maybe even cool your homes or your office complex. Well, there have been few studies on the exact same process for mines, even though there are certainly and most assuredly desirable ground temperatures in our mines. There are abundant sources in many of our mines, if not all of them, of underground water. There's extensive underground excavations, thereby not requiring the drilling of any new boreholes. And therefore, there's plenty of opportunity, if investigated further, to take advantage of what are called open-loop geothermic processes to help reduce energy costs at our mines. There is one mine, happily, in Canada, where this was at least tried, and indeed it is still being used, and that's the Spring Hill mine in Nova Scotia. There remain, however, many unanswered questions, and the true performance of that is unclear at this point, and whether or not that performance can be optimized is unknown. It is hoped, by virtue of this project, that data from there, as well as data from a number of operations throughout Western Europe, shown here, can be accessed, collected, analyzed, and used to develop sophisticated computer simulation techniques that will help identify ways to draw more attention to the potential benefits associated with open loop geothermal opportunities in underground mines. So the research objectives here, as with the other, are to access data and determine whether or not performance can be improved or optimized, to determine whether, in fact, there's enough geothermal energy associated with abandoned and indeed working mines that can, in fact, be a resource for helping to offset current energy costs, and whether or not this technique can, in fact, be used not only in mining infrastructure, that is in underground mines, but in the plants on surface, such as the processing plants that are often associated with these mines. Another solution to addressing the issue of horrendous energy costs associated with ultra-deep mining potentially may be to simply look at existing operations where freezing plants or not are in place, and whether those processes can be optimized. So, for example, this project, which actually has 2 parts to it, is being looked at by by a team at Laurentian University, working with Dean Miller, and it's trying to determine whether or not, in the process by which normal refrigeration plants on surface or underground at mines can in part be helped at the point where vapor is compressed early on, if in fact that vapor compression cycle were to be powered using wind energy. Very simple, but potentially very significant in terms of the energy reduction possible by simply looking at that system or that process in this way, because compressing that vapor at the early part of that cycle is energy intensive and thus costly. So can a conventional refrigeration compressor at that stage in this cycle be powered using wind energy? Because in the end, the product of that cycle is chilled water, which has many, many uses in hot, deep underground operations. The second part of the study that is underway there, which has in part been alluded to already by Dean, is to look at those mines where ice stopes currently exist. Dean highlighted that at Frood Stobie in Sudbury, and there are other mines where ice stopes exist, for example, Kidd Creek in Timmins. Can they be looked at, and can the processes that have been known for years and years and years, with the benefit of today's knowledge, but specifically with the benefit of today's computer simulation technology, can that process be improved so much so that a significant energy reduction contribution can be made by those same approaches that have been around for many, many years? Well, I think the answer is believed by the researchers involved here to very much be in the affirmative. If you look at a nice stope, which is shown, you won't see the details here, in diagrammatic form in the top left there. It really, as explained by Dean earlier, presents many opportunities to not only help cool mines in summer, but warm those same mines in winter, particularly if involved with those stopes is something called a bulk air cooler. So with the benefit of something called CFD modeling, or computational fluid dynamics modeling, it is possible for us to look at what is effectively an old technology and to imagine new designs for what future ice stopes may wish to involve, so that the very positive impact in both summer and winter of using them can be realized. Dean already alluded as well to something called the NEHEA, or Natural Heat Exchange Area, at the Creighton Mine in Sudbury. This, by the way, could equally well apply to any any underground mine which started its life as an open pit and which now has what's called a glory hole at surface. That is a caved open pit into the top of the underground operation. That rubble contained in the bottom of that pile, as has already been pointed out, has actual value in terms of what it can do to air temperature that passes through it, whether it's in summer or whether it's in winter. And at Creighton, where this particular glory hole is substantial in size, that measurement on the right-hand side there is 450 meters, is connected to the existing Creighton underground via a series of tunnels and access drifts and what are called trenches, all of which are controlled by, in this case, 96 doors or ventilation doors. And so, quite reasonably, the people at Creighton might wonder how the decisions regarding how to use this system and when or not those doors should be open or closed would be helpful. And so the Morocco team, working with Dean at Laurentian, have been working over the course of the last 3 years and continue to work on simulation techniques using today's computer technology to try and model as closely as possible what in fact is measured as happening in the underground at Creighton Mine, and imagine this could be at any underground operation. And what this graph on the top right serves to do, if you can see, it's comprised of blue, green, and red lines. What it serves to do is indicate that the modeled output, in this case, of today's modeling simulation software is virtually identical to what the actual measured variation in temperature is underground in the Creighton Mine. So the model is well calibrated, it works, it appears to be able to mimic closely what in fact is going on there. So that provides us an opportunity to help impact decisions, to optimize how that resource, that rock pile, can better be used to cool the underground and heat it at times at the Creighton Mine. Remember, there is no mechanical refrigeration system in place at this mine, yet this mine is down at 8,200 feet. So this stuff is important there. So that modeling has served to help realize on the right-hand side there an additional 3 megawatts of available coolth by simply helping to drive decisions regarding how that whole system is operated in the underground mine. It is felt that that can be improved further using CFD approaches, and the team is closely working on that right now as part of the UDMN project being supported and coordinated through SEMI. An interesting one is whether or not we think liquid air has a role to play, not only in how we cool air in our underground mines, but how we power our equipment. Think about that for a moment. Liquid air, once it is allowed to expand, expands at a very, very significant rate and to a very, very significant volume. Some 700 times, by the way, in terms of volumetric expansion, is possible when that happens. Can that do mechanical work? It absolutely can do mechanical work. Can that involve driving turbines, which in turn drive ventilation fans, which, because they're powered by liquid air, also serve to not only move air, but cool it as they do that? We believe that is the case. Can that same technology, if properly used, help to drive, for example, LHD equipment in our underground mines or utility vehicles in our underground mines? Absolutely. The technology already at a smaller scale is proven to be able to do that. The issue is, can in fact we deliver and store to our deep underground mines liquid air in a cost-effective way that, if put to work in this manner, helps solve the problem, if not solve entirely the problem, of heat generated by LHD fleets and equipment fleets in our underground mines, and the need for expensive ways to mitigate that risk. There's a project looking at just that at UDMN right now, and it's just in its early phases. So the value proposition for mines in all of this work, in our opinion, is that it helps identify ways in which we can optimize current and long-standing practices, while at the same time helping us to explore and potentially exploit new approaches, all focused on lowering ventilation costs, improving the quality of our air, limiting our greenhouse gas emissions, thereby providing, hopefully, a greater social license to operate, which, as we all know, will help sustain our mines, our mining communities that rely on them. The other suite of projects, and there's only 2 in this case, in theme 2 has to do with the electrification of underground mine fleets and what role that might be able to play in helping to reduce energy consumption by largely reducing the ventilation requirements in our deep mines. And so the problem associated with LHD fleets and in our underground mines, as has been stated several times, those problems are manifold. I'm not going to repeat them. You now know that they have to do with the amount of heat generated. If, by the way, you've ever stood in even a not-so-deep mine in an area, a confined area where an LHD is operating, let's say even something as small as a 3-yard scoop, you'll know exactly how much heat those things are capable of generating almost instantly in your workspace. But there's a whole range of issues associated with the current way in which we move equipment in our underground mines, and there are costs associated with that, not only in terms of dollars and cents, but in terms of the well-being of our workforce. And so what can we do about it? Well, it may well be that we have to somehow or other encourage and enable the greater and broader use of electrically driven fleets in our underground mines. Now, it's not that this is the first time in which this has been done. It's been done in part already. For example, there's a suite of underground LHD trucks and scoops operating at a mine in Creighton Lake. There are already in several mines for the last 10 or more years, there have been electric underground LHD pieces of equipment, most of them tethered, as you can see in the bottom right-hand corner there, which have had varying degrees of acceptance and buy-in by operators, both on the equipment itself and mine operators themselves. But generally the sense among operators has been, this is a little too awkward, this is a little constraining, this is something which we don't feel is at a sufficiently advanced technology readiness level for us to whole hog employ it at this point in time. So there's a bit of pushback or resistance in the deep mining community on electric vehicles, but I think that's changing. I think for those that are designing deep mines at the present time, a very serious question that they're asking is whether or not those deep mines can in fact be all electric. Has the technology advanced so much, and we've heard something about that over the last couple of days, that in fact now it is possible to do with electric-powered vehicles what even 5 years ago was not possible. I think there's a greater acceptance that the answer to that question may just be absolutely, or at least we're very close. So the solution we feel at SEMI through the UDMN program is that it's important for us to support some projects that are looking at the development of battery electric drives and battery electrified equipment pieces in our underground mines. It's important that we facilitate the taking advantage of recent developments in battery and electric motor drive technologies, and that we work with developers of those technologies and of equipment fleets built around them to ensure they have the design attributes which make them specifically usable in ultra-deep mine environments. By that I mean they're built to ensure that they're corrosion resistant, for example, that they generate themselves as little heat as possible, that the electric or that the logistic support required for them is minimal. And that's in fact what we're doing. All of this on top of the benefits of using electric versus diesel underground equipment that we've heard a ton about over the last 2 days, some of which is listed on the right there. All of this has the benefit of reducing emissions, reducing heat created, and consequently reducing the need for expensive and very costly ventilation systems, both from a CapEx and OpEx standpoint in our deep mines. It's fair to say, as I mentioned a few moments ago, that some senior mining operators, as well as some OEMs, are very seriously looking at this at the present time. So in conclusion, and I believe that's my last slide, I think it's fair to say that we believe at SEMI and through the ultra-deep mining network that there are important contributions which we can help make happen through the network of partners we're involved with that will be of relevance to ultra-deep mine operators for many years into the future. The particular baskets of projects that we have selected to work on are all about optimizing cooling solutions for deep mines and trying to ensure that using electrified vehicles at least gets a fair shake going forward. Thanks very much indeed.